All right, today I'm going to talk about 8.5 alternating series. To begin with this, I want to return to a series we dealt with earlier in the chapter, the series 1 over n, also referred to as the harmonic series. When we first did this numerically, so once again grabbing our calculator, those of you who have the newer version of the calculator, you do the math 0. And I enter larger and larger numbers, so starting at 1 and then going to like 10, 100, 500, 1,000. What we saw when we looked at that numerically was that that did go to infinity. It wasn't necessarily a very fast-moving infinity, but it would grow without bound nonetheless. So that diverges. Today what we're going to talk about is alternating series. So far the series that we dealt with were always positive. Alternating series have the effect of the first term is positive or negative, the next term is the opposite, so on and so forth. So for instance, in this case, I wrote out the first few partial sums. If I plug, that shouldn't be -1. So if I plug 1 into this thing, I'm going to get -1 to the second power, so that's going to be positive, and then 1 over 1 is 1, okay? And then what happens is, on the next term, so I have my positive 1, I plug 2 into that, well now that's raised to an odd power, so we're going to get a -1/2. And then that's just going to keep going on and on like this. So when this is raised to an even power, it'll be positive. The next one will be raised to an odd power, it'll be negative. And by the way, there's a couple of different alternators. The most common you're going to see is either -1 to the n plus 1, or you could see -1 to the n. If I had -1 to the n, that would just change this. The first term would be negative, which is something that we will see as well. Okay, so these are what are referred to as alternating series because the value that alternates between negative and positive. All right, so what I did with this one was I wanted to look at our partial sums. So this one, of course, diverges, okay? But when I put the alternator in here, look what happens. So I started with 10, and actually quite quickly sort of looks like it's going to converge. If you want to compare it to the original one, I would suggest maybe doing that. You'll see that this doesn't happen at all. Those numbers keep growing. But we see very quickly that this thing is going to converge. So what I would say here is that, and by the way, this is an approximation. This is not proof. You can never use the numerical stuff as proof of a convergent series. But I can approximate this thing. S sub n would be approximately, let's call it 0.6926. And that would be our approximate sum. Okay? So why does this alternating effect cause a series that without the alternating effect would diverge, would then converge? And I think if we kind of think about what's happening here, if we look at these partial sums and we look at the number line, I think it's kind of, you can kind of see what's going to happen here. So our S sub 1 is just 1. So this is S sub 1. Okay. Now what I'm going to do, if I think of A sub n is equal 1 over n, all right, if I subtract, or if I do A sub 2, right, I'm going to subtract 1/2. So that goes to here. So this length we'll call A sub 2. And that gives us S sub 2. S sub 2 is 0.5 here, right? And then what happens after that is that we're going to add A sub 3. And A sub 3, we're adding a third. So if we add a third, right, we're going to go over here somewhere. And that's A sub 3, okay? And then this is going to be my S sub 3, which is what, about 0.86, something like that, 1 minus 1/2. Okay, now, and then this is going to keep going on. So if I'm going to do S sub 4, right, I'm going to subtract A sub 4, and this is going to be S sub 4. So if you think about what's happening here, all right, now keep in mind we have an approximation that's somewhere in here. So the actual sum, okay, the actual sum, which we don't know analytically what this is, the actual sum is somewhere in there. It kind of gets caged by this alternating effect. And so this, if you think about what's happening here, because each new term is less than the one previous, what's happening here is we're always adding or subtracting a term that is smaller than the one prior. So what will happen is, so for instance, S sub 1, and then I subtract A sub 2, I jump the sum. But then the next term is going to be less than, okay? And then the next term will be less than that. So it's just going to keep going like that for for eternity. It's just going to keep leapfrogging this. It basically gets caged up, so it has to converge. So this alternating thing forces this thing to converge, okay? And that is the alternating series test. So I'm going to write up what exactly we look for. First of all, our term has to be positive without the alternator. Each new term has to be less than the one previous, okay? And we'll talk about that. And ultimately, this thing has to go to 0, right? It can't get to a certain point, like 1, because then it's just going to keep jumping back and forth. But if this thing goes to 0, then it is going to converge, and that is the alternating series test. Okay, so let me write that up. Oh, by the way, this example, we're going to return to this example. We're going to talk about this approximation. So if you just want to mark this, we're going to return to this after we do a couple examples. Because the alternating series, not only can we do an approximation, we can talk about how accurate that approximation is in a way that we haven't been able to do up until now. Okay, let's get down the alternating series test in our notes. The alternating series test, which I'll refer to as AST. So given a series, and first of all, this alternator, as I talked about before, another form of this alternator would be -1 to the n plus 1. Some other ones that you may see that do the same thing. So it's any term that one term's positive, the next is negative, positive, negative, et cetera, et cetera, et cetera. If I gave you something like cosine of pi n, that does an alternator because you plug in 1, you get pi, that's -1. And then another one is the sine of pi n over 2. So these all could be possibilities for this alternator. And then some other terms. So basically the way we do the alternating series test is we really isolate this thing right here, or excuse me, the A sub n. Now the thing is, basically 3 conditions have to be met for this to be convergent. The first is, first of all, A sub n always has to be positive. So if there's something that's not positive there, we want to bring it into the alternator to ensure that it's still alternating. So we don't want to have something that sort of counteracts this. For instance, if we had a term that ended up causing this always to be negative, or excuse me, even or odd, then it could sort of counteract that alternating effect. So we need that A sub n, that isolated part, to always be positive for at least the values greater than 1. The next thing is the limit of A sub n has to go to 0. And then usually if this is true, this is going to follow, not always, but basically each new term has to be less than the one previous. This is what's called monotonic. If you think about it in terms of a, monotonic decreasing, if you think of it in terms of functions, we're just talking about a function that's strictly decreasing, right? Each new term is less than the one previous. I guess it's technically less than or equal to, but generally we're talking about less than. And this has to be true for some n greater than n. And what I mean by that is, it wouldn't have to happen right at 1, as long as it happens at some point. So if it spent some time, like, increasing, that would be okay, as long as it gets to a value, and then from there, each new term will be less than the one previous. Now, what I'll tell you is that this is usually a pretty easy thing to prove. 3 is usually obvious. If it's not obvious, we're going to have to kind of look at derivatives and things like that. However, that's sort of rare, and I'll talk about that. So generally speaking, this is an easy thing to prove, and it's going to, usually if the limit goes to 0, this is going to be true. Okay, so if as long as we meet all those criteria, then our series converges by the alternating series test. Okay, by the way, really when it comes down to it, you're really going to look at A sub n, and A sub n, if it goes to 0, typically this thing will converge. If A sub n doesn't go to 0, okay, we already know it's divergent, right? Because if A sub n doesn't go to 0, that means it's going to diverge by n term. The alternator isn't going to change that, right? The alternator will cause it to oscillate between values, but it's not going to converge. Okay, so let's do some examples using the alternating series test. Okay. So here's our example. We're going to prove this thing either converges or diverges. Really, it's as soon as we see that alternator, it's really quick. Typically, if that thing goes to 0, which it does here, it will converge. If it doesn't, then it's going to diverge by in term. And that's really, as soon as we put that alternator in it, it makes it a lot simpler. We don't have to go through all those other tactics to see what's happening. So right off the bat, and by the way, without the alternator, this thing would diverge because of P series, P is less than 1. Okay, so basically all I do is this. I say, okay, my A sub n, which is equal to the non-alternating part, right? 1 over n to the 1/3. Well, that's greater than 0, at least for n greater than or equal to 1. Okay, so that's the first thing. 2, okay, the limit as n goes to infinity. There's no proof here. We can see this easily. The bottom grows, the denominator grows without bounds, forcing this thing to 0. Boom. And then the final thing is, and this one, understand this. This right here, n plus 1 to the 1/3 is going to be less than or equal to 1 over n to the 1/3. I'm going to take the equal out of there. I'm going to go with the stronger statement just because I can. Let me point out that we know that this is true simply because 1 is in the numerator, right? So the larger number is always going to be over here in the denominator because raising something to the 1/3 is 1 to 1. Those values are going to sort of stack up in line. So if I have 4 in the denominator versus 3 in the denominator here, 3 to the 1/3, obviously this is going to be less than because you're dividing by a larger number. This is a very obvious result. There's nothing more you have to say about it here. Where this gets tricky, and I'll probably do an example of this in class. I don't think I'll get to it in this video. I won't get to it in this video. But if there's something in the numerator, then it can be a little bit more complicated, and then we have to do some calculus, some sort of derivative analysis to determine that it is decreasing. So n is greater than or equal to 1, so our series converges by the alternating series test. Okay, and that's it. Let's do one more example, and then we'll go on to absolute versus conditional convergence. Okay, example 3. So I wanted to give you a look at something that has an alternator but diverges. It's usually quite simple. Look at the non-alternating part. Unless it's a very, very rare thing. If that thing goes to 0, this thing will converge. If that thing does not go to 0, it's going to diverge. And why does it diverge? It diverges by n term. I don't actually have to talk about the alternating series test. The limit as n goes to infinity. And you can either isolate this. It does not make a difference. So n squared minus 2, that's equals 4/3. That is not equal 0, so this thing diverges by n term. It makes no difference that it has an alternator. Now, even if I consider with the alternator, if I use the strict definition, I want to point out we still get a limit that does not go to 0. So what if I left the alternator in that? How is this going to impact this limit? So what will happen is, if you think about it, it's going to alternate, it's going to sort of skip back and forth between, as we get higher and higher. When this thing's even, it's going to be going to 4/3, positive 4/3. When that thing's odd, it'll be negative 4/3. So as time goes on, as we go farther and farther along, as n gets larger and larger, when this is even, it'll get closer and closer to 4/3. On the other side, it'll get closer and closer to negative 4/3. So this just simply would not exist. That's still not 0, right? Does not exist, does not equal 0, so it still diverges by n term. So, just using this is perfectly fine, and that's how I do that. We're done, okay? So as soon as we see that alternator, typically, it's really this simple. If that thing goes to 0, it's typically going to mean it converges. If that thing doesn't go to 0, it's going to mean it diverges by n term. End of story. Oh, okay. So now what we're going to do is we're going to return to that example 1, and we're going to talk about how we know with alternating series how accurate our approximations are. Okay, let's return to our example 1. So we started off investigating these way back at the beginning of the chapter just by running the program in our calculator and plugging in larger and larger numbers and approximating. So in this case, we get an approximation using the partial sums to 1,000, and that gave us an approximation of 0.6926. So the question becomes, how accurate is this? In other words, what's the error of our approximation? So just a couple of terminology things for this class. You might have done error in science class. Often you do relative error. In this class, we're always just talking about the difference between the actual and the approximation. So let's say we call S the actual sum. Now, we don't even have access to the actual sum here. We're just going to use this logic that we talked about before so we can at least know how far that is from the actual sum. So in this class, error, okay, is going to equal the absolute value of the actual sum minus our approximation. So in this case, our approximation is S sub n. Now, just some terminology here. One of the things that we typically refer to is if we technically the error will be all of the terms past. So it will be like 1001 to infinity. This is what's called the remainder, R sub n. You don't have to worry too much about this yet. This comes later in the chapter, but just to lay the groundwork here. So our error is equal to the absolute value of what we didn't include, which makes sense, right? Okay, excuse me. Okay, so now let's talk about what the error is here. And so the nice thing about the alternating series is we can kind of think through it, and we return to sort of the logic I said before. So S sub 1 is at 1. Then we subtract A sub 2, which takes us to S sub 2, which is 0.5. And I'm not going to go through the values each. So then if I go the S sub 3, I add A sub 3. Now the thing I got to keep in mind, A sub 2 is greater than A sub 3. All right? Now, then it starts this leapfrogging effect, where it keeps going back and forth across the sum, but it gets tighter and tighter each time. The sum is somewhere in here. Okay? So the sum is somewhere in there. Okay, so what's going to happen is, so let's say I approximate S using S sub 3. So let's say I approximate S by S sub 3. Here's what's going to happen, right? So I'm going to subtract A sub 4. Well, realize that our error, right, the difference between S sub 3, so this would be our error between S sub 3 and S itself, that would be our error, is actually going to be less than the next term, right? Because keep in mind, we're going to leapfrog that when we subtract the A sub 4. So the error is actually going to be less than the next unused term. And that's true for any of these values. So the great thing about alternating series is that our error will be less than our first unused term. Now, if that term is positive, I'm assuming we isolated the A sub n, right? So we're talking about the all positive thing. Otherwise, we bound that in absolute value. So this is given that the series is a convergent alternating series. So in other words, A sub n is greater than 0, number 1. 2, the limit as n goes to infinity of A sub n is equal to 0. And 3, A sub n plus 1 is less than or equal to A sub n. And this is at least true at some point. Okay? So now what I know is my actual sum, okay, S. I don't know what that is, but I know the difference between this is less than the first unused term. So this is my approximation, and I know the error. I don't know exactly what the error is, but I know it's less than the first unused term. So what's the first unused term? It's 1 over 1001. Okay, so 1 over 1001, let's just, consider that, how accurate this is within the scope of this class. So that means our error is less than 0.3000999. Okay, so what that means is it's within the bounds. Normally when we do approximations, using our calculator, we want to be accurate to 3 decimal places, this would be accurate to 3 decimal places. So that is a pretty good approximation. So the moral of the story is when we're dealing with an alternating series, even though we don't know exactly what the sum is, we have this really good way to bound up the error, right? We know the error is going to be less than that first unused term as long as it's a convergent alternating series. Okay. The next thing I'm going to talk about is absolute versus conditional convergence. Okay. The last thing we're going to talk about today is absolute versus conditional convergence. First of all, there's this theorem listed in the book as 8.16. Basically, if you take the absolute value of whatever you have in here. So if you think about this thing as having like an alternator, okay, and we're going to look at some examples which hopefully will clear this up. But if we bound this thing in absolute value, if this thing converges, then the series converges as well. So for instance, if I had a series, well, let's deal with that in examples. So if, well, let's talk about that real quick. Just kind of a side example, just to give you some perspective. Let's say I was dealing with the series -1 to the n plus 1 of 1 over n squared. Well, this does converge by alternating series test. I could go through that alternating series test. This is always greater than 0. It limits to 0. And finally, each new term will be less than the one previous. However, if I bound this thing in the absolute value, okay, well, then the alternator simply goes away. It's always going to be positive. Well, if you look at that, that thing converges, right? P equals 2, which is greater than 1, so this thing converges. So it converges by P series. That means the series converges. So that original series, if we don't need the alternator and it still converges, then the original series converges as well. I don't need the alternating series test. Now we have a specific name for this. This is what's called absolute convergence. It's going to converge whether the alternator's in there or not, whether we use the alternating series test or not, because it converges by P series. We don't need the alternator. So that's absolute convergence. It doesn't need the alternator, which should be an absolute value, in order to get it to converge, right? Now, what conditional convergence is something that doesn't converge without the alternator. So, for instance, the example 1 we talked about, right? We had the series. This was our first example today. Well, we know that if I bound that in an absolute value, right, P is equal to 1, this thing diverges. So, but it still converges conditionally, because as long as we have that alternator, it's going to converge. So that's absolute convergence and conditional convergence. Now let me just be clear. If the question is, does the thing converge or diverge, I don't have to think about this at all. I could use alternating series test for both. However, there will be sections where they ask specifically, does it converge absolutely, does it converge conditionally, or perhaps diverge. Okay, so let's look at those examples. Okay. So example 4, here's our series right here. Does this series converge absolutely, conditionally, or does it diverge? So the first thing we want to realize is that this thing is an alternator. Sine of n over pi, sine of n pi over 2. If we plug 1 into that, it's going to be at the top. That's y, that's 1, negative 1, 1, negative 1. So it does the same thing as if we had negative 1 to the n plus 1. So in this case, you know, our term here, if we want to rewrite this, and it's really up to you, you know, we could actually rewrite it like so. It means exactly the same thing. I just want us to get comfortable with these because we could see something like that. Okay, so what is this thing going to do if we do the absolute value of this, right? So if we do the absolute value, let me point out that we get a series that we know is going to diverge. Because even though it's not directly P series, I can, oh, by the way, if I don't want to do the limit comparison test, you could do the limit comparison test here, do the whole compare it to 1 over n. Let me point out, this is actually equal to, these are exactly the same, 1 over n if n starts at 2, right? Those are exactly the same. It makes no difference. So this thing diverges. If you want to do the limit comparison test and don't like doing that, that's fine. This thing diverges P equals 1 by P series. So now it's either going to converge conditionally, right, because it has the alternator, or it's going to diverge. Those are the only options. So you first consider, what if we took away the alternator? Is it going to converge or diverge? So this thing diverges. So then I go to the alternating series test. So once again, our A sub n is equal to 1 over n plus 1, which is greater than 0. So that's 1. 2, the limit as n goes to infinity of 1 over n plus 1 is equal to 0. Nothing I have to show there. And then 3, 1 over n plus 2 is definitely less than or equal to 1 over n plus 1. So, converges, sorry about a squeaky marker, converges conditionally by the alternating series test. Okay? So if it converges conditionally, that means that we bounded an absolute value and it diverged, but then when we consider it with the alternating using the alternating series test, it converges conditionally. In other words, if you need the alternating series test in order for it to converge, if you need that test, then it converges conditionally. All right, let's look at a couple more examples. Okay, example 5. So this one is going to converge absolutely, and the reason why I know it's going to converge absolutely is if I bound this thing in absolute value. By the way, you need the parentheses here. -1 to the nth does not equal the quantity -1 to the nth. So make sure that you are putting that in parentheses. If you do this instead of that, it will cost you points because it does not mean the same thing. Okay, so what is this equal to? Now I'm going to write it in a form that we can quickly see why this thing is going to converge absolutely. So I'm going to call this 1 over e. That's all to the n, right? So now what I realize is this is geometric. Keep in mind, if we were trying to find the sum of this thing, I want that first term to be 0 here. We don't need that because we're just talking about convergence. So we know the absolute value of r, which is equal to 1 over e. E is roughly 2.718. That's less than 1. So converges absolutely by geometric series test. In other words, we could use the alternating series test to prove convergence, right? Because it would still meet those criteria. But we didn't need the alternating series test, therefore it converges absolutely. Okay, one more example. You can probably guess what this one's going to do, and then that will be it for today's video. Sorry, this one's a little bit longer than normal. Okay, final example for the day, example 6. You probably guess what this is going to do. So just a reminder, example 4 converged conditionally, example 5 converged absolutely. So of course this is going to diverge. And you can see it right away. Like I said, when it has an alternator, it's very simple. If that other term goes to 0, it will converge by alternating series test. If it does not, it's simply going to diverge. It doesn't matter if we're talking about absolute convergence, conditional convergence, it just diverges. So the limit as n goes to infinity of n squared over 3 n squared minus 2 is equal to 1/3. That does not equal 0, so diverges by nth term, and you are done. So that is 8.5, alternating series test.